Hey there, let's talk about something we see literally every single second of our waking lives. Light. We think we know it, right? It turns on, it turns off. But it turns out, light has a secret life, one that's way weirder and more amazing than you probably think.
So you probably learned in school that light travels in a straight line, like a beam. And for the most part, yeah, that seems to check out. But is that really it? Is that the whole story?
And look, for a lot of stuff, thinking of light as a simple ray works great. It's why you can explain how a mirror works. Bam, rays bouncing off. Or why a straw looks like it's bent in a glass of water. It's easy, it makes sense. But this is where things start to get interesting. Because then you see things like the beautiful shimmering colors on a soap bubble or on the back of a CD. And for things like that, the simple ray model just completely falls apart. It has no explanation. So what is going on? Well, it seems light is living a kind of double life.
And this gets us right to the heart of the matter, a puzzle that scientists argued about for a long time. Two totally different ways of thinking about light.
So on one side, you've got ray optics. That's our old friend, the straight line model. Super useful for mirrors, for lenses, simple stuff. But on the other side, you've got this wild idea called wave optics. This says light doesn't travel like a particle, it travels like a wave, rippling across a pond. And this model, it explains all the weird stuff, the soap bubbles, everything, perfectly. So, which one is it?
The breakthrough, the key that unlocks this whole mystery, comes from a really elegant idea. It's called Huygens principle, and it's going to completely change how you see light.
Okay, that sounds super technical, I know. But hang on, the core idea is actually pretty simple. A wave isn't just one big thing moving. It's more like a chain reaction, where every single point on the wave is kicking off a brand new tiny little wave of its own. This is the perfect way to picture it. You drop a pebble in a pond, right? You get that circular ripple spreading out. Now, what Huygens principle says is to imagine that every single point along the edge of that ripple is also a tiny source, creating its own little circular ripple. And all of those tiny new ripples add up to create the next big ripple you see. It's kind of mind-blowing.
And of course, in physics, we have a name for these ripples. We call them wave fronts. All it means is that it's a line where every part of a wave is at the same point in its cycle, like the very top crest of a wave in the ocean. All right, so if light is a wave, does it always have the same shape? Nope, not at all. And it turns out the shape of these wave fronts tells you exactly where the light is coming from.
For instance, a tiny little point source, like a single light bulb, is going to send out waves in every direction. That creates a perfect sphere of light expanding outwards, just like our pebble. But a long, skinny source, like a fluorescent tube light, that creates wavefronts shaped like cylinders, wrapping around the tube.
But here's a really important one. What happens when the light source is super far away, like a distant star? Well, those giant spherical waves travel so far that by the time a tiny piece of them reaches us here on Earth, the curve is so gigantic it looks completely flat. We call this a plane wave, and you see it in physics diagrams all the time.
So, we've got this powerful new wave model. We know it explains all the weird stuff the old model couldn't, but this is the best part. It doesn't throw the old model out. It actually explains why the old model worked in the first place.
This right here is the big aha moment. The reason this wave idea is so powerful is that it gives us a much deeper understanding of all of light's behaviors, even the simple stuff we thought we had figured out. Let me show you what I mean. Check this out. This is what's really happening when light hits a mirror. Those flat wave fronts come in and hit the surface. Then, following Huygens' principle, every point on that mirror spawns a new little wavelet. And when you add all those new wavelets up, what do you get? A brand new, perfectly reflected wave going off in the other direction. It's the physics behind the bounce. Or how about this? Refraction, light bending as it goes through a prism. As the wave fronts enter the glass, they slow down. You can literally see them get squished closer together. That slowing is what causes the entire wave to pivot and change direction. Then, when it comes out the other side, it speeds up again and bends back. It's such an elegant way to see exactly why light bends. And finally, a lens. A lens is just a cleverly shaped piece of glass that slows down the middle of the wavefront more than the edges. And what does that do? It takes a flat, incoming wave and reshapes it into a curved, spherical wave that collapses down to a perfect focal point. It's not magic, you're just reshaping the light itself.
So, this wave model is obviously incredibly powerful. But to get those cool shimmering patterns we talked about, the phenomenon we call interference, well, we need one last piece to the puzzle.
And that piece is called coherence. For two light waves to create those stable, predictable interference patterns, they have to be coherent. All that means is they need to have the exact same frequency and be perfectly in sync with each other. Kind of like two singers holding the exact same note in perfect harmony.
Because if they're not coherent, if the frequencies are all over the place, the waves are just a jumbled mess. They'll still overlap, sure, but you won't get those beautiful, clear patterns of bright and dark spots. For that, you absolutely need coherence. It's the key.
Wow. Okay, we've come a long way. We went from thinking light was a simple ray to seeing it's a complex, beautiful wave. And this wave theory explains so much. It really feels like we finally cracked it, right? We found the final answer. Or did we?
Because just when you think you've got physics all figured out, it throws you a massive curveball. There's this thing called the photoelectric effect. It's basically light hitting a piece of metal and knocking electrons off of it. And for some really deep reasons, the wave theory of light utterly fails to explain it. The master key we just found won't open this door.
And that leaves us with an even bigger question than the one we started with. We asked if light was a ray and discovered it was a wave. But what happens when being a wave isn't the whole story either? That question would spark a whole new revolution in science and launch us into the age of quantum mechanics.